Two topics that students often have trouble with when they're first learning probability and statistics is independence and mutually exclusive events, and how they're different from each other and when to apply each. So in this video, I kind of want to step you through a couple examples so that maybe you might understand the difference. Okay. So with independence, the typical problem that we're going to do is where maybe we're rolling a die 3 different times. Okay. And each roll of the die is sort of like an independent trial. Okay. That one roll does not affect another. So in that case, the 3 die rolls are independent. Okay. So the roll of die 1 does not affect the roll of die 2, and that does not affect the roll of die 3. And for that reason, we can ask things like, what's the probability that, let's say, roll 1 equals 5, and roll 2 equals 3, and roll 3 equals 2. Right? Each one of these events, so this is one event, here goes another, and here goes another. The event, or each trial of rolling a die, is independent. Because of that, this probability is just equal to the multiplication of each individual probability. So again, the probability that roll 1 equals 5 times the probability that roll 2 equals 3 times the probability that roll 3 equals 2. Okay. So again, in this case, maybe a way to think about it is we talk about maybe independent trials. Okay? That's a good way to maybe work through it. And if you have different trials, you're in most cases you're going to have independence between each trial. All right. All right. The other place, or the alternative topic that we should talk about, is mutually exclusive. Now, mutually exclusive, it typically involves a single trial. Okay? So here we're talking about rolling a single die. Okay? And those outcomes, right? So the possible outcomes for a die are 1, 2, 3, 4, 5, and 6. They are mutually exclusive from each other. And the reason is, if I only roll the die once, it has to be one of these numbers. I can't roll the number 2 and 4 at the same time, right? It has to be one of them. So in that sense, each of these outcomes are mutually exclusive. Now, we can have a compound set of outcomes that are mutually exclusive. So for example, the outcomes that the rolls are odd or even are also mutually exclusive. Okay? So the set of rolls that are odd, okay, is 1, 3, and 5. Okay? And the set of even numbers, or rolls, are 2, 4, and 6. Okay? So in that sense, 1, 3, and 5 is mutually independent from 2, 4, and 6 because they don't have any overlapping values. Okay? So if I were to ask, what's the probability that the roll of a single die is odd and the roll is even? Well, I can't have both at the same time. Right? And so what that means is when we take the intersection, so if we take the intersection of 1, 3, and 5, and we intersect it with 2, 4, and 6, well, that's just equal to the null set. Okay? So that probability is going to be 0. Okay? And so this is the reason why we care about mutually exclusive events. or one reason. Now, we can certainly imagine a case with a single die where we don't have mutually exclusive events. Right? So let's say I were to ask the question, what's the probability that my roll is odd and let's say it's less than or equal to 3. Okay, so let's actually rewrite this to be a little bit more clear. So the probability that the roll is odd and the roll is less than or equal to 3. Okay. So the roll is odd can happen a few different ways. 1, 3, and 5. While the roll is less than or equal to 3 can happen by 1, 2, and 3. Now, if we look at these two sets, they are not mutually exclusive because they have some values in common. Okay. So when we take the intersection of these two events, we're left with the probability that the roll is 1 or 3. Okay. Now, at this point, the probability that a roll is 1 or 3 is mutually exclusive, right? Because what we can have is that's the same thing as saying the roll is 1 or the roll is 3. Both can't happen at the same time. And so when you have mutually exclusive events like this, you can actually add up their probability if you're taking the union. So in this case, we'd get 1, 6 plus 1, 6. All right. So let's sort of summarize that. So focusing on mutually exclusive. So let's say A and B are two events that are mutually exclusive. If I ask you what's the probability of A and B happening at the same time, right? Rolling a 1 and a 5 at the same time, you can't do that. This is going to be equal to 0. Now, if I ask you what's the probability of rolling an A or a B, in that case, if A and B are mutually exclusive, that's equal to the probability of A plus the probability of B. Okay, and that's the sort of this example we just did here. All right. Now again, this involves the case of, we can think of it as like a single trial typically. That's not always going to be true, but in a lot of times we're talking about a single trial. Okay. Independence we usually have multiple trials. Or another case is we have different random variables. And I'll give an example of that. All right. When we have independence, let's say I ask you to calculate what's the probability of A and B. When you have independence, then that's equal to the probability of A times the probability of B. Okay. If I were to say, what's the probability of A or B? Well, that's equal to the probability of A plus the probability of B minus the probability of A and B. Now, in that case, we can just substitute what we had in here. And use the law of independence. Okay. it doesn't really help us too much. Now, the same thing actually happened in this mutually exclusive event, right? Because the OR condition always has minus the probability of A and B, okay? The issue is, however, we know that the probability of A and B is equal to 0. So this is equal to 0, so usually we don't even worry about it. And that's why the union of A and B for mutually exclusive events is just the probability of A plus the probability of B. All right. So again, if you have a single trial and it's mutually exclusive, then that tells you something about what A and B is. But more importantly, it tells you how you can add up A or B. When you have independent events, or usually you want to think about as multiple trials, right? So you're rolling a die 5 times. Usually you're going to see stuff like this, where you say probability of A and B is equal to the probability of A times the probability of B. Now, I gave an example of independence with multiple die. Okay? And that sort of makes sense in terms of trials. Now, sometimes another way that we can have independence has to do with different random variables. So one way we can think about it is, let's say I were to survey a bunch of people, and I were to ask them, what kind of pet do you have? All right, so that's a reasonable question. And maybe another question I might ask them is, are you left-handed? We could certainly imagine that whether you're left-handed or not has nothing to do with the type of pet. So there's no relationship here. So there's no relationship between whether you write with your left hand or not and the type of pet that you own. In this case, we would say pet ownership, right? So the type of pet you own is independent of left-handedness. Okay, so if this was true, if we were to ask what's the probability of owning a dog and being left-handed, we could just apply the rule of independence when it comes to probabilities and say, well, that's just equal to the probability of dog times the probability of being left-handed. Okay. So here's an example where we have independence because we have sort of two questions or two random variables that have nothing to do with each other. Right? Now, let's pretend we can certainly imagine a case where they do have something to do with each other. Let's say I were to ask two questions. One might be, what is the probability you like, or I'm going to do a survey, okay? And I'm going to say, do you like math? And are you an engineer? Okay. You can imagine that your answers here are probably highly related to each other. Okay. If you like math, there's probably a better chance that you're an engineer. And if you don't like math, well, you probably shouldn't be an engineer. And so when we ask questions like, what's the probability that you like math and you're an engineer, we can't just say that's equal to the probability of liking math times the probability of being an engineer. This is not correct, so don't ever do that. Wrong. Okay? These are clearly probably related to each other. Now, the closest thing we might be able to do is we might be able to use conditional probability to solve this problem, because we know that the probability of A and B, or A given B, is equal to the probability of A and B all over the probability of B. Yeah. So maybe, let's say I tell you, well, the probability that you like math, given that you're an engineer, is about 75%. And I also know that the probability you're an engineer, or a student is an engineer, is about 10%. Okay? So if I wanted to calculate what is the probability of liking math and being an engineer, well, I could just rearrange terms in our conditional probability equation to get that answer. Okay? That's just going to be equal to the probability that you like math, given you're an engineer, times the probability you're an engineer. Okay. So in this case, it would just be 0.75 times 0.10, which is 0.075. Okay. So hopefully you'll see we went through all sorts of different ways that we can talk about independence and mutually exclusive events. Usually, so let me sort of step you through this again. If you have multiple trials, there's a good chance those trials are going to be independent. So that means you can multiply probabilities out for each trial. Okay? If you have a single trial, like rolling a single die or something like that, you're probably going to be solving a problem that includes some sort of mutually exclusive event. Okay? Now, that's not always true. You can certainly, if you have compound events, so here the roll is odd, can happen multiple different ways, and the roll is less than 3, that can happen multiple different ways. In that case, if there's overlapping, then they're not mutually exclusive, even though it's a single trial. Okay. We also talked about how you could have independence when you have different random variables, right? So you're asking different probability questions. So what kind of pet you own is independent of whether you're left-handed or not. Now, there are certain probability problems where two pieces of information are related, like do you like math and are you an engineer? In those cases, I'll either give you some sort of probability, but you should probably think about using this conditional probability equation somewhere. It's a good chance it's going to come up unless I give you this joint probability. Okay? I tell you what is the probability of A and B. All right, so hopefully that helps some of y'all in understanding mutually exclusive events and independent random variables or independent events.